This lecture is about some very general ideas related to group theory. So that's part 2.5, and I want to talk about homomorphisms. So let's suppose you have two groups. So suppose you have two groups, G1, G2 are groups. And the question is, okay, how they are related? So how are they related? So we know there are various ways in which groups can be related. For instance, G1 can be a subgroup of G2, or G1 can be isomorphic to G2. But definitely there is something more general than that. And you can have in mind a picture where G1 is a certain group of symmetries of some polytope, for instance. And G2 can be, some other group which looks kind of roughly the same, but maybe slightly smaller or slightly bigger. Or it's a group of the same polytope, but you ignore, for instance, so this can be symmetries of polytope where you color vertices in certain way, and this is where you ignore colors, and so on. So definitely in such cases, these two groups will be related. And isomorphism and subgroup is just two special cases of how groups can be related to each other. And now I want to discuss something more general. So let's start right on with definition. So definition is that a homomorphism phi from G1 to G2 is a map, so just function, such that for every two elements xy in G1, we have the following identity: phi of xy equals phi of x, phi of y. Okay, so as for the case of isomorphism, it's really easy to see that then phi of identity will be identity, because you can plug in x equal to y equal to identity and cancel phi of E because you're in group G2, and phi of G inverse is, x inverse is phi of x inverse. So I don't write this as requirements in the definition, but that will just follow. So this is the major kind of formula. Okay, so what does it mean? So it means that there is a map from G1 to G2 which respects operation. So at least it sends product to product. And of course, we'll see various examples of such maps. Some of them will be very trivial and they won't say anything about G1 and G2. But there are actually very interesting examples as well. And then if there are what's called non-trivial homomorphisms between groups, it basically tells you that the groups are related in a certain way. So let's look at some examples. So example number one, examples. So the first example is example usually people start with in math, the most simple, the most boring. So let G1, G2 be any group. So one can look at phi from G1 to G2. And it is defined by the rule phi of x equal to identity for any x in G1. And this is identity kind of as element in G2, of course. So if you draw your groups as sets, so the second group has identity, and what it does, it just maps everything there. That's a very boring homomorphism. It exists between any two groups. And of course, the property is really easy to check. If you take any two elements here, this and this part will be identity. And second example is also not particularly interesting for us, because definitely an isomorphism is a homomorphism. So you have already seen similar definition in linear algebra. So in linear algebra, you have a notion of a linear map between two vector spaces, and this is pretty much the same idea. So operation preserving structure. Except for vector spaces, there are a lot of different linear maps. They basically correspond to matrices, and between groups, the question is much more subtle. So finding interesting homomorphisms is a kind of a deep question. So let's continue this list of examples, and I want to look at the following picture. So let's consider S3. And I will construct a homomorphism from S3 to S2. So that looks a little bit weird at first. So to every permutation of 3 elements, I want to assign a permutation of 2 elements. And the idea is that if you want to come up with a homomorphism, you better have some. So of course I can just look at all my elements in a group and start figuring out what this homomorphism should do. But let me do something different instead. So let's look at a triangle. So we already discussed this kind of picture of S3 several times. Imagine we have a triangle with maybe vertices A, B, C, and then we have 3 reflections with respect to these lines of symmetry, identity, rotation by 120 degrees, rotation by 240 degrees. So I want to construct a homomorphism to S2. And S2 clearly has 2 elements, so let me call them something like E and let's say R. Maybe R is a bad letter. Okay, R. So, and then I will do as follows. So I will send, so my group consists of 2 pairs. So I will send these rotations to the identity. And here I have these reflections. And I will send them to this R. And the fact that it is a homomorphism means that if you have 2 rotations, you multiply them, you get a rotation. So identity, identity, identity. So let me just write it down. So it's basically the following observation, that if I take multiplication table of my group and I write here all rotations, including identity, and here over all reflections with respect to these 3 lines, and I organize my table in this kind of block structure, then I will see that composition of 2 rotations is a rotation, rotation and reflection gives a reflection, reflection and rotations give reflection, reflection and reflection gives a rotation. So basically, and of course this exactly means that this is a homomorphism. So I denote this element by E and this element by R, and then I see multiplication table for my group with 2 elements. So basically, homomorphism, if you wish, is basically the statement that you can rearrange your multiplication table so that you have this kind of block structure. So if you just know that an element is here in some block and here in some block, you can see where it will go when you multiply. And then there is this kind of block multiplication group structure on these blocks. So we'll think a little bit more about this multiplication table interpretation a little later, but that's an example of a homomorphism. And of course, it's very natural to ask, okay, these elements rotate triangle, and what do these elements do? And then if you think a little bit about that, so if you look at 3 rotations, then these are elements which you can do if you just take your triangle as a rigid body, move inside your plane. But 3 symmetries, you cannot do like that. You need to go outside of the plane. So if you think of your map as a transformation of a plane to itself, S2 corresponds to 2 elements, and this is depending on what they do to your plane. So basically, so this phi equals to E, or phi equals to R. So if R2 is flipped, and this if R2 is not flipped. So basically, the permutation of 2 elements is a permutation of basically 2 sides of the plane. Either they both stay fixed or their role is exchanged. So there is something very interesting about this construction, and you see it's not completely obvious. It tells us something fairly deep about the symmetries of a triangle. And next time, or maybe this time after next time, we'll discuss a generalization. So actually, this is a special case of what is called a sign, and there is always such homomorphism from Sn to S2. So there is always this map preserving multiplication, sending permutations to this two-element group, and then you can divide all permutations into two types, even and odd, depending on where they go. Okay, so as we already discussed back when we looked at first examples of groups, there are basically two maybe main examples of groups: symmetry group and linear group, the group of isomorphisms of a vector space or otherwise invertible matrices. So let me discuss the second example right now. Okay, example 4. So let's take as G1, we will take GLN of F. And I remind you that these are n by n invertible matrices with coefficients in F. And F here is a field, and if you are confused what a field is, please read about that. You can use Wikipedia for that. So this will be G1, and G2 will be just multiplicative group of a field, so the same elements, this is just field without 0, and operation here is multiplication. And then, so there is this homomorphism, which is called determinant. So determinant is a map which to every invertible matrix associates a number, and the map takes a matrix A to its determinant. And of course, the property that it's a homomorphism is just a statement that determinant of A times B is determinant of A times determinant of B. And when you study determinants, you might see that as, you know, some complicated theorem you learn late, and it looks already kind of complicated and so on. It's actually the main important property of determinant. It sends product to product. It's a homomorphism, and of two groups. And from group theory perspective, that's one of the major maybe properties of GLN of F. There exists such a homomorphism. So we will discuss it more from this perspective. Meanwhile, I want to look at last example for this class. So there will be more later on, of course. So okay, so we discussed that there is this homomorphism from S3 to S2, and I said from any Sn to S2 there is a homomorphism. What about other groups or Sn? So maybe there are so many homomorphisms between Sn and Sm. So indeed there is something. So there exists a homomorphism from S4 to S3. So this is something interesting. So you have a permutation of 4 elements, and you want to assign to it a permutation of 3 elements. And so let me call it phi. So the problem with this homomorphism is that actually it's not unique. There are several of them, and it's not surprising because it's an easy exercise. So let me leave it as an exercise. Is that so? If you have 3 groups, G1, G2, G3, and you have phi psi, and if phi and psi are homomorphisms, then if you do first phi and then psi, that's also a homomorphism. So composition of homomorphisms is a homomorphism. That's pretty trivial. And so, for instance, I remind you, every group has automorphisms, being isomorphisms with itself. And so if you have this phi, you can, for instance, compose it with conjugation here, or compose it with conjugation here, and you will get more like different homomorphisms. And so it's not so simple to write down all of them, so we will do it. And so there is no canonical way to choose it. So for instance, if I just take a matrix like 1, 2, 3, 4, sending to 2, 1, 2, 3, 1, 4, actually it's unclear where it goes. There are choices. And so if you want to actually construct one, you of course can try to say, okay, let's send this permutation to this permutation, somehow play with it a little bit and eventually come up with one of them, but it's not so simple. So let me explain to you a conceptual way to do it. So what is S4? So S4 is, it's a group of bijections of set with 4 elements. So we have set with 4 elements, and then we can permute them in some way. So say take, I don't know, this one goes here, this one goes here, this one goes here, this one goes here, or something like that. That's what an element in S4 looks like. Okay, so here is an idea. So if it is a bijection, I can look at some additional structure on my set. So what is a structure on a set? It's a hard question. I can't say there is a unique definition, but for instance, I can look at the following thing. So let me call this set, for instance, A. So there exist 3 ways to partition A in 2 sets of equal size. So divide by 2 basically. So indeed, so if you have your set 1, 2, 3, 4, you can write it as 1, 2, union 3, 4, or 1, 3, union 2, 4. So these are just, subsets, right? These are just elements. And finally, I can write the same thing as 1, 4, union 2, 3. And these are the all ways to divide your set with 4 elements into 2 equal parts, disjoint. So let me label these ways to do it by 1, 2, and 3. And then here is an idea. So imagine you do a bijection. And this bijection will somehow relabel your elements 1, 2, 3, 4. So now 1 goes to 2, 2 goes to 3, 3 goes to 1, 4 goes to 4, for instance, like this one. And then there are these 3 ways to divide them into 2 parts, and they will be also permuted. So for instance, if you do this permutation, it's really easy to see that what will happen. So if you do permutation with 1, 2, 3, 4 goes to 2, 3, 1, 4, it's really easy to see what happens with these 3 subdivisions. So 1 goes to 2, 2 goes to 3, so this subdivision will become this one, because 1, 2 will go to 1, 3, and 3, 4 will go to 1, 4, sorry, 1, 2 will go to 2, 3, this one, and 3, 4 will go to 1, 4. So basically 1 goes to 3. And then we can just figure out, okay, so 2 will go to 1, 3, 2, 4, will go to 2, 1, 3, 4, which is 1, and 3 will go to, okay, so 3 is 1, 4, 2, 3, 1, 4 goes to 2, 4, and so it's 2. And so you see that if I permute my elements, my 3 subdivisions also got permuted. And of course, it defines a map from one group to another. To every permutation here, I will associate a permutation here. And then I recommend you to think it through a little bit. So it's a homomorphism. It sends product to product. Why? Because imagine you permute your elements using some bijection. And then you do another bijection. And you want to know what happens with these 3 partitions. And then if you see what happens to them after first permutation, and you know what happens to them if you do the second permutation, under composition, you just compose permutations which happen to them. And that's exactly the definition of a homomorphism. So it's basically the statement. And why it's not unique? Because when I did that, there was some choice involved. So I labeled my decompositions into this by these 3 Roman letters, and I can do different labeling, and this will correspond to conjugation here. So we'll see this example again. It's not very simple, but it's a very important, basically canonical example of what a homomorphism might look like. And actually, these are all homomorphisms from S4 to S3, and in some very particular sense, if you just want to look at homomorphisms between different permutation groups, there are not much. If the case is not for 3, then, and the groups have different number of elements, so it's not an automorphism, then the only option is this sign homomorphism or trivial one. And, so basically, if you want your homomorphism to be surjective, then it will be only this one or sign from Sn to S2, or isomorphism from Sn to Sn, basically nothing else. So one can understand all homomorphisms between symmetry groups pretty easily. And that is interesting, especially because you see the sporadic one. So this is kind of a special one. It doesn't sit inside any family. And that's why it appears a lot in math under different names, and we will see it appearing a few more times in this course. So next I want to talk a little bit about kernels of homomorphisms, images, and other basic definitions related to homomorphisms. Okay, so first I want to talk about kernels. So kernel is something you know from linear algebra, and basically it has the same meaning. So G1 to G2 phi is a homomorphism. Morphism. And then so kernel ker phi is a set of elements in G1, set of elements G, well, let's say, G in G1, such that phi of G is identity. Identity as element in G2. So just all elements which go to identity. Of course, as you might expect, so there is a following proposition. So I will formulate 3 statements. So first, kernel of phi is a subgroup of G1. So it's a subgroup, and this is really easy to see. We'll do it in a second. So second, and this is analogous to the fact that if you have a linear map between 2 vector spaces, kernel is a subspace of the first one. So second is that phi is injective. So sends different elements to different elements, if and only if kernel of phi is consisting just of the identity element. Identity element is always in the kernel because it's a subgroup and because it goes to 1. So these two are analogous to those properties of vector spaces and linear maps. So the last one is a little bit more maybe interesting. So for every element X inside the kernel and every element G inside the group, G X G inverse is also inside the kernel. So if you take elements, so this is inside a bigger group, right? So if you take elements in the kernel, you can apply this conjugation by some elements. And conjugation is an automorphism, in particular a bijection. And the statement is that whatever conjugation you apply, your elements in your group got permuted, but elements in the kernel stay inside the kernel. So that's very interesting property. And if you if you remember from last lecture, we discussed this idea that basically conjugation corresponds to some sort of relabeling of elements of your group. Like in Sn, we can relabel elements. If we just relabel elements of a set, we permute. And then, I mean, of course, kernel has to be invariant under conjugation because kernel is something which is defined without saying how you label elements of your group. So if you have a group S4 going to S3 and you have a homomorphism, if you have a homomorphism, you don't need to know how you label elements of a set you permute. You will still be able to talk about its kernel, which is a subgroup. And so it means if some element is there, you relabel stuff, it should be still there. So it means that this kernel should be invariant under conjugation. So, and this is very simple to check. So you might think of it as some maybe peculiar property, but actually it's super important. Later on, we will call such groups which are invariant under conjugation, having this property, we'll call them invariant subgroups or normal subgroups of G1. And actually, for every such group, there exists a homomorphism shrinking it to identity. And so basically, to understand homomorphisms, you just need to understand all these kernels of, all these groups having this property. But this will come in about maybe a week or so. For now, let's just prove it. So proof is completely straightforward. So part one, so imagine I have two elements x, y in the kernel, and then I know that phi of x, y, phi of x is equal to phi of y is equal to the identity, then phi of x times y is also equal to the identity, so x comma y, xy is inside the kernel. And now we show that two elements are in the subgroup, so their product is there, so our subgroup is closed under multiplication. And then we also can see that identity is inside the kernel, and similarly x is inside the kernel, then x inverse is also there. So all that is pretty trivial. And this proves part one. So kernel is a subgroup. So part two is, I don't want to, write it into many details, but sort of if you imagine phi of x equals to phi of y, happens if and only if phi of x, phi of y inverse is identity. You can always do such things in groups, but that's the same thing as phi of x, y inverse is inside equal to identity. So it means that x, y inverse is inside the kernel. And from here you can derive the statement, because, if you know that kernel is trivial, it means phi of x equals phi of y, then x equals to y. On the other hand, if you know that kernel is non-trivial, you will get some element which goes to the same element as identity, which contradicts that is an injection. So that's very straightforward. Let me just leave it here. And finally, showing the last part is also simple, because if you just take, so if phi of x equals to the identity, then phi of g x g inverse you can expand. And since it's a homomorphism, we see phi of g, phi of x, phi of g inverse. And at first you might be worried how you exchange it. Group is not commutative in general, but we started with phi of x equal to the identity, so it's killed, and so you get that it equals to the identity. So this one is in the kernel, then this is in the kernel. Very simple. Okay, now let me maybe add one more idea about kernels and say a few words about images, and we finish there after maybe one more example. Okay, so maybe example. So for instance, we can look at our group GLN of F, and we have this homomorphism to F cross, which is a determinant. And so now we can look at matrices. So A are matrices. So, and we want matrices which are invertible and with determinant equal to 1. So such that determinant of A equal to 1. And then I don't even need to say that over F, that they are of size n by n, that they are invertible, because if determinant equals to 1, it means they are invertible. So this is the kernel of my map, and it's a subgroup. So subgroup of matrices with determinant 1, and its name is called SLN of F. So GLN is usually called general linear group. So general linear group, or GLN, and this is usually called special linear group. Linear group. Okay, very simple. So another example might be, So what about S4 going to S3? And so we need to find permutations which fix these three ways to divide elements in pairs. And actually one can check that these are permutation identity, then permutation which flips 2, 1 and 4, 3, permutation which flips 1 and 3, 4 and 2, finally permutation which flips 4 and 1, 2, 3, 3, 2. And this is a group, so this is a subgroup, and that's a kernel. And that's a little exercise, so please check it. So this subgroup is usually called V4, and that's called a Klein's subgroup. So Felix Klein is a great mathematician of 19th century who did a lot to make group theory part of kind of everybody's common knowledge. And he promotes idea that group theory is a way to think about geometry, that a space is basically something plus the group of symmetries it has. And this group is called in his honor, and it has this German name, which I cannot repeat. So this is just kind of old notation for this particular subgroup. So and please check that indeed these permutations leave these three subdivisions on a set of 4 elements into pairs fixed. Okay. So finally, I want to mention one last thing. So if you have another definition. So if you have this homomorphism from G1 to G2 called phi, then one can look at the image. So M of phi, it's called the image, and this is a subgroup of G2. So Y in G2 such that there exists X in G1 such that phi of X equal to Y. And that's really simple to check. So this is there are 2 facts. M is a subgroup of G2, and of course this image equals to G2 if and only if phi is surjective. So exactly as with vector spaces, you have this analog of linear map, homomorphism. You have kernel, analog of kernel. You have image, analog of image. Kernel is identity if and only if map is injective. Kernel is equal to, image is equal to the whole group if and only if phi is surjective. And if you want phi to be bijective, hence an isomorphism, then you need to check 2 things. Image is G2, kernel is G1. So in some sense, image is less important idea than kernel maybe, because kernels actually, as we'll see later, define homomorphisms. And of course, if you have a homomorphism, you can compose it with any inclusion of G2 as subgroup somewhere. You will get more and more homomorphisms from this one. So in some sense, the most interesting are those which are surjective. Okay, so in the next lecture, I want to prove Kelly's theorem. So the theorem you had to prove in homework with this multiplication tables. And now I will use all this language to do it super cleanly.